Today's topic is partition function. In canonical ensemble, identical systems remains in the state of thermal equilibrium with heat source. All the identical systems have same temperature, absolute temperature capital T in canonical ensemble. Consider a system of n particles in thermal equilibrium with heat source of absolute temperature T. Consider one system having n particles and it is in thermal equilibrium with heat source of absolute temperature T. It means its temperature is also T. Suppose particles of the system are distributed in different energy states such that Gi states of energy Ei, there are Ni particles. Write this as small ni. Ni particles are in Gi states of energy Ei. Gi is known as degeneracy of energy state Ei because Gi are the number of energy states having same energy Ei. It is known as degeneracy. So Ni particles are distributed in Gi states of same energy Ei. According to postulate of equal a priori probability, Ni will be proportional to Gi. Ni is the number of particles and these are distributed in Gi states having same energy Ei. And according to Boltzmann's canonical distribution law, this Ni will also proportional to e to the power minus Ei upon Kt, because according to Boltzmann's canonical distribution law, the probability is proportional to e to the power minus Ei upon Kt. So number of particles will also proportional to e to the power minus Ei upon Kt. These are two equations, number 1 and number 2. Ni is proportional to Gi and Ni is also proportional to e to the power minus Ei upon Kt. If we combine these two equations, we find that Ni will be proportional to Gi into e to the power minus Ei upon Kt. Or we can write it as Ni equal to a Gi e to the power minus Ei upon Kt. Here A is proportionality constant. A is constant of proportionality. Since total number of particles in the system is capital N, therefore capital N will be equal to summation Ni. These capital N are total number of particles. These particles are distributed in such a way that N1 particles are distributed in G1 states and 2 particles are distributed in G2 states and so on. So capital N will be equal to N1 plus N2 plus N3 and we write this as summation Ni. Put the value of Ni, capital N will becomes equal to summation A Gi e to the power minus Ei upon Kt. A is taken outside of the summation, then it will becomes equal to A summation Gi e to the power minus Ei upon Kt. Summation here is for I. N upon A. This A is taken to left hand side, then N upon A will become equal to summation gi e to the power minus ei upon kt, and we write this quantity as z. This quantity summation gi e to the power minus ei upon kt written as z, it is known as partition function. Partition function z tells how the particles of a system are partitioned among various energy levels when the system is in thermal contact, is in thermal equilibrium with heat source at absolute temperature T. Now we will find the partition function for monoatomic ideal gas. Consider a system of monoatomic ideal gas in which total number of particles is capital N and volume is V. Let mass of each molecule is small m, write it as small m, mass of each molecule, and this system is in thermal equilibrium with heat source at absolute temperature capital T. It means that temperature of this ideal gas is capital T. Since intermolecular attraction force between molecules of ideal gas is 0, potential energy of the system is 0, and total energy of the system will be equal to kinetic energy. Total energy is kinetic energy plus potential energy. Here potential energy is 0 because for ideal gas there is no intermolecular attraction force between its molecules. So total energy is now equal to kinetic energy. Let coordinates of a particle in phase space is x, y, z, px, py, pz. Phase space is 6-dimensional space. We have 6 coordinates, 3 coordinates for position x, y, z, and 3 coordinates for momentum px, py, pz. Then partition function z is equal to summation gi e to the power minus ei upon kt. Here we put the value of ei. Ei is the energy. Here it is written as entropy of ith particle. Correct it. It is not entropy of ith particle, it is energy of ith particle. Energy of ith particle ei is equal to pi square upon 2m. Energy is equal to kinetic energy. Kinetic energy is half mv square. If we multiply and divide by m, then it will become m square v square upon 2m, and mv is p, momentum, so it will become p square upon 2m. So we write energy in terms of momentum. Energy is kinetic energy half mv square, and it is equal to p square upon 2m. So we write ei equal to pi square upon 2m. Then z becomes equal to summation gi e to the power minus pi square upon 2m kt. And if we have 3 components of p as px, py, pz, then p square will become equal to px square plus py square plus pz square. So z becomes equal to summation gi e to the power minus px square plus py square plus pz square divided by 2m kt. Here gi is the number of energy levels in ith cell, and or we call it as degeneracy. So gi is number of accessible microstates in energy range ei to ei plus dei, or in the momentum range px to px plus dpx, py to py plus dpy, pz to pz plus dpz. Consider a volume element dx dy dz dpx dpy dpz in phase space, volume of a cell in phase space, it is the degeneracy Gi. Volume of a cell in phase space is H0 cube. In phase space, the smallest volume element is known as phase cell. It represents a microstate. So volume of this cell is H0 cube. It is the volume of one microstate. So if we consider this volume element dx dy dz dpx dpy dpz, we divided by H0 cube, then this will give the number of microstates, and it is the degeneracy Gi. Number of energy states having same energy Ei. Here we take energy in this range, in this small range Ei to Ei plus dEi. So Gi, degeneracy, number of energy states in the energy range Ei to Ei plus dEi is dx dy dz dpx dpy dpz divided by H0 cube. Since there are large number of particles in this system, changes in momentum and energy are continuous. So we can replace summation in equation 5 by integration. In this equation 5, for z equal to summation Gi e to the power minus px square plus py square plus pz square upon 2m kt, we write here the value of Gi. From this equation, Gi equal to dx dy dz dpx dpy dpz divided by H0 cube. Put this value of Gi here in this equation, and we can replace this summation by integral. Then z becomes equal to integral dx dy dz dpx dpy dpz divided by H0 cube. It is the value of Gi, and e to the power minus px square plus py square plus pz square divided by 2m kt. Summation is replaced by integral, and we here write 6 integrals. 3 integrals for dx dy dz and 3 integrals for dpx dpy dpz. These 3 integrals for dx dy dz, this will becomes equal to V. It is the volume of the system. So keep separate these 3 integrals, integral dx dy dz. 1 upon H0 cube is constant taken outside the integral, and other 3 integrals are written as integral e to the power minus px square upon 2m kt dpx. First integral in remaining 3 integrals is this for dpx. With this we write the term of px. Term of px here is e to the power minus px square upon 2m kt. In this exponential there are 3 terms. One is e to the power minus px square upon 2m kt. Second is e to the power minus py square upon 2m kt. And third is e to the power minus pz square upon 2m kt. So these are written as 3 separate integrals. Integral e to the power minus px square upon 2m kt dpx, integral e to the power minus py square upon 2m kt dpy, right here as dpy in place of dpx, and the third integral is integral e to the power minus pz square upon 2m kt dpz. So the first 3 integrals, triple integral dx dy dz, it is equal to V, volume of the system, and value of each integral It is not volume of each integral, it is value of each integral in this limit. It is not circuit. In this limit minus infinity to plus infinity, the value of each integral is 2 pi m kt to the power half. It is under root 2 pi m kt. These three integrals for dpx, dpy, dpz, value of each integral is under root 2 pi m kt. So z now will become equal to v upon h0 cube 2 pi m kt to the power 3 by 2. This is the partition function for monoatomic ideal gas. Now we will find entropy in terms of partition function. Consider a system of ideal gas in thermal equilibrium at absolute temperature T, having total number of particles which are identical and distinguishable particles. Total number of particles is capital N and total energy is E. These particles are distributed among microstate of energy E1, E2, E3, EI and so on in such a way that corresponding number of particles be N1, N2, N3 and Ni and so on, and corresponding number of microstates which is degeneracy is G1, G2, G3, Gi and so on. So total number of particles are capital N, total energy is capital E. Out of these capital N particles, N1 particles are distributed in G1 states of energy E1, N2 particles are distributed in G2 states of energy E2 and so on, or in general we can write as Ni particle are distributed in Gi states of energy Ei. Then according to Boltzmann's canonical law, Ni will proportional to Gi and Ni will proportional to e to the power minus Ei upon kt. Then Ni equal to A Gi e to the power minus Ei upon kt. A is constant of proportionality. Number of accessible microstates corresponding to the macrostate N1, N2, N3, Ni and so on. This is the macrostate. N1, these are number of particles having energy E1. N2, these are the number of particles having energy E2 and so on. Ni is the number of particles having energy Ei. And for this macrostate, number of microstates which is known as thermodynamic probability, and we write it as by W. W is thermodynamic probability. It is the number of microstates corresponding to this macrostate N1, N2, N3 and so on. So this number of microstates or thermodynamic probability W is given by factorial n upon factorial n1, factorial n2, factorial n3, factorial ni and so on. In numerator we have factorial n, it is factorial of total number of particles. In denominator we have factorial n1, it is the factorial of number of particles in first box. So it is the number of particles having energy E1. Then we have factorial n2, it is the factorial of number of particles having energy E2 and so on. And with this we have G1 to the power n1, G2 to the power n2 and so on, and Gi to the power ni. Because N1 particles are distributed in G1 states and 2 particles are distributed in G2 states and so on. So we write this as G1 to the power n1 into G2 to the power n2 into G3 to the power n3 and so on, and Gi to the power ni. So W, we write it as factorial capital N, and the remaining terms, which are multiplication of several terms, are written as pi I, as we use summation for addition. This symbol pi I is used for multiplication of several terms. G1 to the power n1, G2 to the power n2, G3 to the power n3, Gi to the power ni is written as pi I Gi to the power ni. If we write I equal to 1, we get the first term G1 to the power n1. If we write I equal to 2, we get the second term. And pi I is the multiplication of all these terms for I equal to 1, 2, 3, 4. Similarly, in denominator we have factorial n1, factorial n2, factorial n3, and it is written as pi I factorial ni in denominator. So W, thermodynamic probability, we write it as factorial capital N into pi I Gi to the power ni upon factorial ni. Now W is equal to factorial n pi I Gi to the power ni upon factorial ni. If we take log on both sides, then log W, we write it as ln W. Ln is log. It is log on E base. So log W will be equal to log factorial n. First term is factorial n, so its log is log factorial n. Then we write plus. Then log of pi I Gi to the power ni, it will becomes equal to summation I ni log Gi. Pi I is now replaced by summation I, because log A into B into C is equal to log A plus log B plus log C. So if we have multiplication of several terms and we take log, then this multiplication is replaced by plus sign. So we now use the summation sign for plus. So log of pi I Gi to the power ni, pi I is replaced by summation I, and log of Gi to the power ni is ni log Gi. So we have plus summation ni log Gi. Then in denominator we have pi I factorial ni. So log of this term will become minus summation I log factorial ni. Now we use Stirling formula for log factorial n. Stirling formula for log factorial n is this, that log factorial n equal to n log n minus n. Then we have second term plus summation ni log Gi. Then in third term we also use Stirling formula for log factorial ni, and this becomes equal to ni log ni minus ni. This now becomes equal to n log n minus n plus ni log Gi, and in last two terms we separate these two terms, open the bracket, then this will becomes minus summation ni log ni and then plus summation ni, and this plus summation ni will becomes equal to plus capital N. It is the total number of particles. So this plus summation ni is plus capital N, and it is cancelled by this minus n, and the remaining terms are n log n plus summation ni log gi minus summation ni log ni. From equation 1 is this ni equal to a gi e to the power minus ei upon kt. If we take its log, then log ni will be equal to log a plus log gi plus log e to the power minus ei upon kt, and log e to the power x equal to x. So log e to the power minus ei upon kt will becomes equal to minus ei upon kt. So if we take log of this equation, it will give log ni equal to log a plus log gi minus ei upon kt. Put this value of log ni in this equation 3, then we get log w equal to n log n plus summation log gi minus summation ni, and in this last term we put the value of log ni, which is log a plus log gi minus ei upon kt. This becomes equal to n log n plus summation ni log gi. Then open this bracket. We have the three terms. First is minus summation ni log a, second is minus summation ni log gi, and last is summation ni ei upon kt. These two terms are cancelled out, minus summation ni log gi and plus summation ni log gi. And in this last term, summation ni ei, it is the total energy E. N1 particles have energy E1, so their energy is N1 E1. N2 particles have energy E2, so their energy is N2 E2. In this way, total energy capital E is N1 E1 plus N2 E2 plus N3 E3, and it is written as summation ni ei. So in last term, summation ni ei is written as capital E. So this last term will become plus E upon kt. So log w now will become equal to n log n minus in this term we write summation ni as equal to capital N. So with log a minus capital N log a. With log a we have minus capital N. Summation ni is capital N. So here we have to put capital N before log a. So correct this. It is not minus log a. It is minus n log a. And the last term is plus E upon kt. Summation ni ei is capital E, total energy. So correct this equation. It is n log n minus n log a plus E upon kt. Capital N is taken common from first two terms. Then these first two terms will become capital N log capital N upon a. Log n minus log a will becomes log n upon a. And last term is E upon kt. And n upon a is z, partition function. So it will become equal to n log z plus E upon kt. So we find log w, and now we can find the expression for entropy S, because entropy S is equal to k log w. Put the value of log w in this expression. So S will becomes equal to k, and log w is n log z plus E upon kt. So S will become equal to k n log z plus E upon t. It is nk log z plus E upon T. Remove this bracket. Correct this here. It is nk log z plus E upon T. There is no bracket. For molecules of ideal gas, energy of each molecule is 3 by 2 kT, 3 degrees of freedom for translational motion. So total energy E will be equal to 3 by 2 n kT for 1 mole. For 1 mole gas, number of molecules will be Avogadro number capital N. And if we consider we can assume it as total number of particles is capital N. Do not consider as 1 mole. Energy of each particle is 3 by 2 kT. So energy of capital N particles, capital E, is 3 by 2 n kT. Then from this relation we can find the entropy for ideal gas. It is nk log z plus E upon T. There is no bracket. Put here the value of E equal to 3 by 2 n kT. Then we can find the entropy for ideal gas. For 1 mole ideal gas, N will be equal to Avogadro number. Then nk will becomes R, universal gas constant. Then entropy will be equal to R log Z plus 3 by 2R. Now we find the internal energy in terms of partition function. Mean energy of a molecule, E bar is the mean energy. It is total energy upon total number of particles. Total energy is summation NiEi and total particles are summation Ni. Total energy E is equal to summation NiEi. It is equal to N1E1 plus N2E2 plus N3E3 and so on. And in denominator we have total number of particles. It is N1 plus N2 plus N3 and it is written as summation Ni. So it is E bar, mean energy, and according to Boltzmann's canonical law, Ni is equal to AGI e to the power minus EI upon KT. So we write this value of Ni, then E bar will becomes equal to AGI EI e to the power minus EI upon KT divided by AGI e to the power minus EI upon KT. Put this value of Ni here in equation 1 and we get E bar, mean energy, equal to this term. A is cancelled out in numerator and denominator. Then mean energy E bar becomes equal to summation Gi Ei e to the power minus Ei upon Kt divided by Gi e to the power minus Ei upon Kt. Now partition function Z is equal to summation Gi e to the power minus Ei upon Kt. So the term in the denominator is Z, partition function. But in numerator we have Gi Ei e to the power minus Ei upon Kt. So to find the term in numerator, we differentiate this Z with respect to T and find delta Z upon delta T. If we differentiate this function capital Z with respect to capital T, it will becomes equal to summation Gi and differentiation of e to the power minus Ei upon Kt with respect to T will gives e to the power minus Ei upon Kt, and along with e to the power minus Ei upon Kt we have minus Ei upon K, the term with T we have minus EI upon K, and the differentiation of 1 upon T is minus 1 upon T square. This will gives delta Z upon delta T equal to 1 upon KT square summation GI EI e to the power minus EI upon KT. And from this relation we find summation GI EI e to the power minus EI upon KT equal to KT square delta Z upon delta T. So this is the term in numerator here for E bar, summation GI EI e to the power minus EI upon KT. Numerator term, it is equal to KT square delta Z upon delta T. So E bar now will becomes equal to KT square delta Z upon delta T divided by Z, or we can write it as E bar equal to KT square delta upon delta T log Z. Delta Z upon delta T upon Z can be written as delta upon delta T log Z. So mean energy E bar is KT square delta Z upon delta T divided by Z, or KT square delta log Z upon delta T. So this is the mean energy in terms of Z partition function.